Good afternoon, everyone. My name is Longfei Chen from Tsinghua University, China. The first author, Jialai Wang, have some conflicts, so I will give us this talk. Today, I will talk about improving machine learning-based binary function similarity detection by exercising and deprioritizing control flow graph features. So the binary function similarity detection has witnessed great progress recently. They often choose control flow graph, also we call CFG, as an important feature to learn out of functions, as CFG characterize the control dependencies between basic blocks. However, the exact role of CFGs in model decisions is not explored, and the extent to which CFGs might lead to model errors is unknown. So this work takes a first step towards exercising the role of CFGs in these solutions, both theoretically and practically, and promotes their performance accordingly. Next, I will provide a detailed introduction. So machine learning-based binary function similarity detection, also we call ML-BFSD, has proven effective in a broad spectrum of applications, such as patch analysis and vulnerability discovery. So typically, it takes a pair of functions as input and computes a similarity score between them. In this process, the primary role of models is to embed target binary function into a latent vector space, where geometric metrics are adapted to compute function similarities. To establish a good function representation, models should learn function semantics as comprehensively as possible. To achieve this goal, many models learn based on control flow graphs. Control flow graphs depict control dependencies between instructions, which aids in learning function representations. For example, some tools split function semantics into basic blocks and generate features for each of them. After that, they use graph neural networks, also we call GNN, to learn relationships between blocks on CFG. So it seems appropriate in this way. However, we found that it struggled to learn the relationships between instructions in distant basic blocks, and changes in the function's CFG structure can significantly impact the model's judgment. Realizing that CFGs can influence how models learn function representations, we sought to explore the role of CFGs in model decisions and whether reliance on CFG could lead to model errors. To clarify the role of CFGs, we first use explanation methods to explain model behavior. Existing research indicates that we can use interpretable machine learning models to approximate the decision boundary of the target model. Once approximated, we can observe the feature importance within the machine learning model to reflect the corresponding feature importance in the target model. We employ this methodology and design explainer to explain the role of CFGs in model decisions. However, this approach presents two main challenges. The first one is how to specify features to represent functions. And the second one is how to approximate the target model. So firstly, we are the first to apply explanation methods to the BFSD domain. And the existing explanation approaches lack feature specifications, particularly regarding the features depicting CFGs. So this hinders explainer from scoring the importance of each feature. Some explanation methods directly score function bytes, which is pointless in our task, since CFG can hardly to directly characterize using bytes. So to overcome this challenge, we specify human-readable features to represent functions. Each feature represents a component affecting model decisions, and it can be scored by explainer to intuitively reflect its importance. So there are two types of features, semantics and CFG. Semantic features encompass various common instruction types, such as call and arithmetic instructions, while the number of nodes, A's, and the graph similarity belongs to CFG features. So using the methods above, we got the importance score of different features on each solution. We choose 11 state-of-the-art work to test. In this chart, the results prove that the top 8 methods are heavily rely on graph itself. So to have a deeper analysis of CFG, we propose a new algorithm called the deltaCFG, which can modify pair of functions CFG identical or different without changing function semantics. There are 2 main challenges. The first one is the manipulation should be automated since we need to large-scale evaluation. The second one is, as we need to verify the importance of CFGs, the manipulation should preserve the original semantics, which avoids introducing alerted semantics that affect model decisions. To address the above challenge, we designed 2 algorithms, the basic block match algorithms and the edge match algorithms. For detailed information, please refer to our paper. So we use the deltaCFG to manipulate the CFGs of function pairs to be either identical or different, and then observed its impact on the model results. Specifically, we randomly select 5,000 pairs of functions, which are semantically identical. Then we modify their CFGs to be different and observed whether the model misjudged them as semantically different. We also modified 5,000 different semantics pair CFGs to be identical. So the experimental results showed in the chart, and ER means error rate of models. When the CFG changes, many models misjudge a significant portion of the function pairs. This indicates that over-reliance on CFGs can lead to serious model security issues. So for instance, real-world code refactoring could cause the model to make errors. So why do these models heavily rely on CFGs? We conclude 2 potential reasons that cause the over-reliance. First, we found that these BFSD solutions have design flaws that undermine the learning of semantics, resulting in the over-reliance on CFG features. For example, Gemini and Dexter manually specify features, as they neglect the order of instructions when defining manual features, which leads to information loss. So second, we note many solutions use a biased training set. The function pairs in the training set can be generally categorized into 4 types. We found that numerous pairs belongs to type 1 to 3, while only a small amount of them belong to type 4. Note that only function pairs in type 3 and 4 have the same CFG. However, type 3 is much more common than type 4, which can cause models to tend to identify functions with the same CFGs as similar, namely over-reliance on CFG features. The remaining question is, why shouldn't model rely on CFG features? So we believe that the essence of constructing function representation lies in understanding the semantics of functions. Semantics are determined by both instructions themselves and their context, that is, relationships between instructions. Thus, models need to learn not only the instruction, but also their context. However, CFG can represent a certain aspect of function semantics, but not all of them. For example, GNN-based method typically exercise at learning relationships between instructions within basic blocks that are directly connected. For instructions located in distinct blocks that are not directly connected, it is generally less effective for GNN to capture relationships between them. So this implies that learning based on CFGs could limit models' understanding in instruction context. With deltaCFG, we can easily create the type 4 data, same CFG with different semantics. So therefore, we created a balanced training dataset and fine-tune each model to enhance their performances. The experimental results show that by reducing the bias in the training dataset, the model's accuracy in the BFSD task can be effectively improved. And also, we checked their error rate and found that after fine-tuning, the model's robustness against CF changes has significantly improved as well. So for the conclusion, in this paper, we focus on CFG features in machine learning binary function similarity detection models. We exercise the rule, apply explanation methods, and reveal the heavy reliance on CFG features in existing models. Also, we propose a new CFG manipulation solution called deltaCFG, which can make different functions CFG identical or different. After that, we improve the performance of our dataset, and and that is what our papers need. Thank you for your listening.